Hello everyone and welcome to the fourth Afterhours session. Today we're going to speak about the LQR problem. Now, our goal right now is to understand what's the meaning of the cost function. What are these terms in the integral? What is this final term? And so on. So, just to remind us what we did in class, we had an LTV system and we had the cost function, and our goal was to find some optimal control, which would minimize this cost function. So I want to start by considering an LTI system and examining each one of these two terms. So let's take n equal to m equal to 2. So we have the state is in R2 and we also have two inputs. So two variables in the state and two inputs. In this case, Q will be this symmetric matrix, R will be this symmetric matrix. And when we explicitly write X transpose QX, this is what we get. So note that here everything is a square, and you have the first term times the second term, which is also like second order, and the same thing here. Now, these are quadratic functions, quadratic forms, and they define paraboloids, which is like balls in three-dimensional space. So for example, for this term, we have what's called the state cost ball. So this is how it looks in three-dimensional space. And similarly, for the control, we have the control cost ball. Now, let's understand what's the meaning of these balls. So let's take a specific moment in time, t. So here obviously the x's and the u's are functions of time when I choose some specific time. So x1 and x2, u1 and u2 just become numbers, and these become constants. So at any point in time we have this, so this term is equal to some constant, and it's basically like taking a knife and horizontally cutting this ball. So basically when we choose some numbers, we will be on one of the ellipsoids seen here, or maybe even better, seen here. So any choice of numbers for x1 and x2, as you can see here, for example, let's say I have x1 equal to 2 and x2 equal to more or less minus 4, then this will be the value. And for this ellipsoid represents all combinations of x1 and x2, which will yield some specific value in the function, which is the ball. So what does it mean in terms of cost? The number itself, so like cx here and cu here, are the cost. So here's an example. So for some specific point in time, the second value for x is 1 and the first value for x is 2. For these values we have cost 16, and this means the cost of being in this specific position is 16. I remind you that our goal is to minimize the cost. Now, there are many combinations of positions, of state positions, which yield the same cost. These are all combinations which will land us on this very, very specific ellipsoid. So everything here is quite symmetric, and our goal is for our state to go down the ball because we want to minimize the cost. Minimizing the cost means going all the way down to the bottom, and clearly the same with the control cost. We want to minimize the costs. This means that our trajectory, or optimal trajectory and our optimal control will have to go down these two balls. Now, what's the meaning of the integral? So, for any specific point in time, we have the cost of the state and the cost of the control. Our trajectory goes from time t0 to times tf, and we just sum up the costs. Okay, now, as we said, what is the optimal trajectory? It's the trajectory that will just go down this state cost ball. Now, the problem is that in order to go down this ball, we need to use the controller, but using the controller means going up the control cost ball. So let's see two extreme cases. Basically, if we do nothing, we take u to be 0, this means that our control will sit at the bottom of the control cost ball, which is good because we minimize the control cost, but it's quite problematic. So if we don't have any inputs, any control, if the system is not stable, the state will go to infinity. So the state will go up the state ball. Now, even if A is stable, so the system is stable, this means that the system asymptotically will go to 0. That's also not optimal because it might go down very, very slowly, and as time passes, we accumulate costs. So maybe the system will go to 0, but it will go to 0 very, very slowly, and we will still have very, very high cost. Now, on the other hand, let's say we want to use the controller aggressively. We will use the controller to push the system down the state ball. So the cost of the state will go to 0 quite rapidly, but clearly we will jump in the control cost ball because we are using the controller aggressively. So what's the solution? Basically, the solution of the Riccati equation gives us the perfect balance between using the controller and making sure the state goes down the ball, and not using too much of the controller to make sure we can slowly decrease the usage of the controller, so the controller will also go down in the ball. So let's see an example. So I have some initial state. The initial state will be wherever it is in the ball. So in this example, it's quite far up the ball. Now, our goal is to make the trajectory go down the ball, clearly using a combination of the natural dynamics and the control. Now, because the initial condition up high up the ball, we are going to need to use the controller. So the initial condition of the controller is also going to be quite up the ball. Now, what's going to happen is at first we need to use the controller quite aggressively to get the state down the ball. So let's see, you can see the state rapidly goes down the ball and the control remains more or less the same. It remains in the same height because we still need to use it quite aggressively. But now that the state is quite low within the ball, we can use less of the control to make sure it steadies into zero. So we use less of the control, so the controller also goes down the control ball, and what will happen is that eventually they will simultaneously reach zero. And this is actually the optimal control and the optimal trajectory, and they minimize the cost function because basically what we see here inside the integral, we consider we just have zero, so nothing. Okay, now what is the meaning of the Q and the R? What happens when we change the values? So let's consider a diagonal matrix Q, just for the sake of example. Basically, the value of Q1 dictates the steepness of the ball along the x1 axis, and Q2 dictates the steepness along the x2 axis. So if Q1 is massive and Q2 is tiny, the ball looks like a long, narrow canyon. So let's see an example. So here, Q1 is equal to Q2, and they're both quite low. So we have quite a shallow ball, which is quite easy to go down. And in any case, the cost is very, very low. Let's only increase Q1. So as we increase Q1, okay, so I need to run this. So as we increase the value of Q1, the steepness along the x1 axis really increases. So suddenly, having a high value in x1 in absolute value costs a lot. So having a -4 costs a lot, having 4 costs a lot. So when we increase Q1, it's like telling the system moving along the x1 axis costs a lot of money. So let's try not to do it. And when Q2 is very low, we can just go along the x2 axis and the cost remains the same, as we can see here. Going from the value -2 and 2, they are all just low. So it's like telling the system, I prefer going on in the x2 direction. Now, in many cases, in Newtonian systems, x1 is usually an indicator for position and x2 is an indicator for velocity. So when I take Q1 to be much greater than Q2, it's like telling the controller, I don't care. Let's say we need to go from point A to point B. I don't care how fast we will do it because velocity is very cheap. Q2 is very small. But it's important that the position will be perfect, because if we deviate from the perfect straight line, it will cost a lot of money. And the same logic clearly goes for the control cost. So if R1 is very massive, in this case, it's like saying using the U1 requires a lot of fuel, a lot of effort, costs a lot of money. And if R2 is small, it means that using U2 requires a small amount of effort. Now, what about the terminal cost? So far, we talked about this integral, but in the cost function, we also have this terminal term. So it clearly also indicates cost, but what's special about it, it indicates cost only at a very specific time, only at t equal to tf. It tells us how much I care about reaching my goal perfectly. So if S is equal to 0, there is no terminal penalty. The controller will just make sure the costs of going from A to B will be low, but we won't really care if we really hit point B at t equal to tf. We will be in the vicinity. Now, when S is very, very large, it's like saying, okay, I want to go from point A to point B, and I want to minimize the costs of going from point A to point B, but it's super important for me to actually, at time t equal to tf, to really hit point B. So, for example, you all probably saw the SpaceX rocket. It's this rocket which goes up vertically and it can actually land itself vertically. So for the rocket, the integral part with the Q and the R, they determine the flight of the rocket. Like how much fuel you want to conserve and the smooth path of the rocket and so on. Now, the terminal cost is like the landing pad. So it's quite obvious in this very, very specific case of the SpaceX rocket, it has to land perfectly vertically. So if it lands a little bit skewed, it will just blow up. So in this case, the terminal cost is very, very high. So you can look at this as like two balls. If S is very, very small, the ball is very, very narrow and wide, and it's basically like saying you can land anywhere in the ball, as long as you're in the ball, it's okay. Now, when we take S to be very, very massive, we make the ball very, 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 very high and narrow. And again, as long as we land in the ball, it's okay, but the ball is very, very narrow, so we have no space for errors. So it's like this SpaceX rocket landing perfectly vertically. Okay, now what about the Riccati equation, why it works, where it comes from? So we saw that if there exists a solution to the differential Riccati equation, then an optimal solution exists and it's unique. The optimal solution is what we see here, and actually the minimal cost is again what we have here. Now this is the differential Riccati equation, and let's understand it together. Basically, the solution P represents a ball which changes over time to accommodate the terms in the integral and the final term with S. So it represents a ball, but the ball itself changes over time. So basically, at any time t, x transpose px represents the total minimum cost remaining until tf. It's basically tell us how much cost do we have left if we go along the most optimal trajectory. So clearly at time tf, we need to actually have our final term cost. So that's why we have this term here. Now, clearly we need to take into account the Q and the R. So you see here we have this plus Q term. This takes into account the state cost. So the state cost makes the ball steeper. And this term over here with the minus, it has this R in it in the B. It takes into account the benefit of control. So this term actually flattens the ball. It represents the fact that we can use our controllers to escape high cost areas. So if we have a very, very good controller, it's quite easy for us to go down the ball. So this term will actually make our, let's call it overall time varying ball P, be shallow. Now, the last term is quite interesting. It actually takes into account the actual system, because the system can be stable, in which case the solutions go to 0, and it can be unstable, in which case the solutions go to infinity, and it can be also marginally stable, so the solution is just it's sinusoidal, so basically it's not going to 0 and it's not going away to infinity. And basically this rotates the ball, because it naturally changes the state variables. And if the system is stable, it helps to flatten the ball. If it's unstable, it makes the ball even steeper. So let's see this really nice animation. So basically this is the animation of the ball generated by P as time goes along. So actually what we see here is the final time. We're going to go back in time. In the final time, this is simply the cone generated by S, but we can go back in time. This is the initial condition, and this is actually the least cost we can have. This is the most shallow the ball can be, and this is why the optimal cost is given here. So the optimal cost is given for the initial time, as you can see here. Wherever we land in this ball, this depends on the initial condition, this will be the minimal cost. Now, as we go along with time, the ball will actually change, transform. It will take account the fact that we need to use energy and cost to stabilize the system and so on. So it will increase, and eventually it will go and merge with the terminal term. Now, what about the optimal control? So basically, we saw earlier that the point of the optimal control is to make the state go down the ball to 0. Now, we know from calculus that the fastest way, or the most ideal direction to move is down the gradient. So if we are on some point in the function, the gradient is pointing at the steepest direction. So if we go the opposite way, that's just pointing at the valley, at the 0. So we would like the cost function, the optimal cost, we would like the optimal controller to always take the system in the direction of minus the gradient. So in our case, the function is x transpose px, the gradient gives twice px, and now let's look at the optimal cost, and we can actually see we have px here, which is the gradient, and the minus. So indeed, the optimal controller is trying to push the system perfectly down the ball, but that's too ideal, because clearly we have two things we need to take into account here. We need to take into account the fact that the inputs reach the system through the matrix B, and we also need to take into account the fact that using the inputs cost us. So basically, this term, which is what we see here, is just projecting this optimal direction in the direction of B, because we can only use the controller as B dictates to us. And also we have the cost. So if R is very, very big, like the fuel is very, very expensive, the inverse of R shrinks the controller. That's why we have the R inverse. When the cost is very, very, very costly, when the control is very, very expensive, the optimal controller will be very, very small, because it costs a lot of money to use it. That's why we have R inverse. So basically, the optimal trajectory, going back here, is just some point in this ball which goes down the ball all the way to 0, but we have to keep in mind that the ball is changing over time. So as the ball is changing, our trajectory goes down this ball, eventually reaching 0. Now, of course, the natural dynamics also take effect, and so on. Okay, so I want to have an example. Consider a drone which is maintained at some constant altitude, so it's somewhere in space, and let's assume it's inside a building, and our goal is to make the drone go down a narrow hallway. So first of all, the motion is governed by Newton's second law, so F equals ma. So if P is the position, F equals ma is like P double dot F over m. Now this is a second order system, we need the first order system, so we define the following state vector. So we have position in x, velocity in x, in y. Our control input is just some force in the x direction, some force in the y direction, and this is the system we have with the following A and B. Okay, so again, as I said, the objective is to navigate a narrow hallway aligned with the y-axis while strictly avoiding the walls located at the x equal to plus minus w. So the width of the hall is twice w, and our goal is to minimize the cost function. Now, how do we take the cost function to accommodate our actual problem? So Q will be this diagonal matrix, and we will take the penalty of going in the x direction to be 1 over w squared. So when w is very, very large, this means the hallway is very, very large. We have a lot of room to go in the x direction, so 1 over w squared becomes very, very small. So the penalty decreases. But as w becomes smaller and smaller, the hallway is very, very narrow, then 1 over w squared is very, very large. So we have a high penalty going in the x direction, and we also take the penalty in position x to be much larger than the penalty in position y, because we want to encourage the system, the drone, to go down the hall, which is the y direction. Now, we cannot just take the penalty of the velocities to be 0, because on one hand I only care about location, I don't want to hit the wall, so who cares about the velocity? But clearly, if we don't give any penalties on the velocity and we say, okay, we can go in any velocity, if we have a very, very high velocity in the x direction, even if we are very, very close and we want to stop, if we are too fast, we cannot stop before hitting the wall. So even though the goal is a spatial goal, so we only care about positions, we can't just ignore the fact that we are moving in speeds as well. Okay, now to make things even more interesting and more related to real life stuff, we can also assume that the input is bounded by some physical limits. So the values of the controller are bounded by some Umax. Now, let me remind you that if we consider the steady state case, then the optimal solution will give us some matrix, constant matrix K. So each entry in K relates to penalties in the xy direction and the xy velocity. And let's just specifically focus about the input in the x direction. So ux will be minus kpx px kvx vx. Now, taking into account the fact that the control is bounded, we have this inequality, and this inequality actually gives us some interesting relation between the velocity in the x direction and the position in the x direction. So the maximum velocity we can travel in when we are in position x along the x-axis is given here. Now, note that if we increase the penalty for the position in the x direction, that is, if we make the hallway narrower, we also increase this weight. And if we increase this weight, then clearly the maximum safe velocity also decreases. So if we make the hallway narrower, the safe velocity in the x direction goes down, and it makes sense. Everything works fine. Now we can plot this problem for some initial conditions. Clearly, the mathematics don't really care about the wall and they don't care about the constraint on the controller, but this is what we have. So the black lines are like the physical walls. So we took W to be 0.5. So the x direction here is position in the x direction, and the y axis here is the velocity in the x direction. Now these dotted red lines, they represent our maximal control. So basically, the optimal control, sometimes depending on the position and the velocity, can be larger in absolute value than our possible control inputs. So, for example, the optimal trajectory is what we see here in gray. Now, as we see here, if we are too close to the wall and we are moving too fast in the y direction, even a very, very strong pull from the optimal controller is not enough to make us not hit the wall. So let's see, if we start here, then the velocity in the x direction is relatively high. We are clearly very close to the wall, and even if we use the maximum of our controller, so we use Umax and minus Umax, still we hit the wall. And what's interesting, that even the optimal trajectory, which we will see here in gray, would still make us hit the wall. So for some velocities and some positions close to the wall, even the most optimal controller cannot help us. Now, what we see here is an interesting case where we cannot actually use the optimal controller, because the optimal controller for these specific values of position and velocity is larger than our Umax or Uminimum. So we would like to travel along the gray lines, which would be going like this, but because the cost of the controller is too high, if the optimal controller is too high, the maximum we can do is to go along this orange route, and yes, even going along this orange route, which clearly, as we enter this safe region, coincides with the optimal route. It's still enough to make us not hit the wall. Now notice, of course, that the goal of the optimal control is always to bring us to the origin. So the origin is, in this case, is just being at 0 position in the x-axis with 0 velocity. Because clearly the most optimal way to go along the hallway is literally to go along the hallway and not to the sides. So our optimal controller will always push us back to the center of the hall and make us just go straight along the y direction, which is basically going straight along the hallway. So this is how we can actually use the LQR problem to solve a real-life problem with constraints. So sometimes we have constraints on the controller, so we cannot actually use the optimal trajectory, but starting from some point like here, we can. So we need to take into account the optimal controller, which is like the thing we do in our notebooks, which is very, very it's very, very nice, but it's not real life. But we also need to take into account our actual real life constraints. Like here, when we are too close to the wall and nothing will help, we will just crash. And that's it for today.